Welcome, I'm Carl Tate. The topic is seafloor spreading and magnetic stripes. We start with a picture of the cover of a book called The History of Earth's Crust, published in 1968, following a conference held in 1966. We see this intriguing picture that we'll dive into here. Here's that picture from a figure published in a paper in the book. And we're looking at magnetic field anomalies offshore of Oregon, Washington, and British Columbia. So here's offshore Oregon, Columbia River. This is Vancouver Island, British Columbia. There's stripes and there's also some symmetry. So we'll look at a cut through here to see what I mean by that. If we look here, we see reds, oranges, yellows, light greens. The pattern is roughly symmetric, meaning if you held up a mirror along this line, you'd see something that looks quite like the other side. Not exactly, but in terms of how complicated the Earth is, this is a pretty symmetric pattern. So this is a pattern of seafloor ages, as shown here in millions of years. And it's this pattern that's roughly symmetric about a spreading ridge, what we know to be the Juan de Fuca spreading ridge, separating the Pacific plate being made on the left from the Juan de Fuca plate formed on the right. This is the kind of pattern, as we'll see, was critical in collecting the data for this in understanding and putting forward plate tectonic theory. But it starts back 10 years earlier, 1958, looking at marine surveying of magnetic work offshore of Northern California. And here we'll have to fill in. It's not as easy to see what's going on in this picture. So we'll start by the scale bar, reminding ourselves that 1 degree latitude is about 100 kilometers to get a sense of scale for what we're looking at. And now here, the plot is solid line contours of regions of positive magnetic measurements, and the dashed lines are negative ones. So we see I've shaded in some regions where we have these bands, long, somewhat narrow bands of positive or normal polarity. And that's what the authors are trying to understand. But really, it starts with just mapping out the seafloor and then standing back to try to figure out the measurements and observations you have. Here's a cross section the authors make from A to A prime. If we look in this cross section, we're now looking at the total field anomaly on the y-axis, and this would be distance along the profile, 60 kilometers here. And so this shows the caption, two-dimensional interpretation of magnetic profile. And the authors interpret that this observed solid line could be modeled by a body shown here on the ocean floor, some anomalous magnetic material shown here. And that gives rise to the dotted lines that's quite in agreement with the observations, making them think, well, maybe this is really what the Earth is like down there. And they said the most obvious and acceptable geological explanation is that the excess material represents lava flows, which have spread out over the floor of the ocean, possibly filling pre-existing troughs or depressions produced by the weight of the accumulating flows. That turns out to be incorrect. Three years later, 1961, figures showing a little more of this, and now instead of the contour lines are just shaded regions. Areas of positive anomaly are stippled, the shaded ones, negative contour lines are broken. So here, basically, you can see again this striping pattern. This is San Francisco, San Andreas Fault. So we're looking west of California at the seafloor and showing a larger version of these patterns. And they write, the anomalies are such as might be expected of slab-like structures underlying the ocean floor. Geological possibilities include basic lava flows, topography of the main crustal layer, and intrusion of ultra-basic material from the mantle. Trying to understand what could make these. That also turned out to be not correct. Same year, 1961. This is now looking similar to what we saw earlier. This is looking at a large region of the magnetic anomaly. And we can see lots of stripes here, lots of complexity, but also definitely patterns of stripes. And they say there is, as of yet, no satisfactory explanation of what sort of material bodies or physical configurations exist to give the very long magnetic anomalies. It has been suggested that there are troughs and ridges buried under sediment, plate-like lava flows that filled older troughs, unique groupings of vertical dikes, high iron content derivatives of weathering that filled older troughs, or a thermal pattern that has highs and lows about the Curie point of ocean rocks. So many creative ideas, yet none of them turned out to be correct. This first statement is true. The authors were acknowledging this doesn't quite make sense with the observations they have. So they were onto something. And it was this critical data set that led to some great discoveries. So meanwhile, starting in that same year, big discoveries were being made. 1961, Dietz hypothesized that the seafloor spreads. And this was based on a recognition that there were major differences between the profile of oceanic and continental crust. And we haven't even talked about these topics, but the point is that he was coming at it from a very different place, but said the seafloor spreads. 2 years later, in 1963, based on measurements of magnetic properties in rocks of different ages, Cox and others said that the Earth's magnetic field periodically reverses, at least over these geological timescales. So pretty radical idea to think about Earth history and its magnetic field changing. And then finally, in that same year, 1963, Vine and Matthews published Magnetic Anomalies over Ocean Ridges, saying that seafloor spreading occurs at ridges, resulting in magnetic striping on the seafloor. And this is what Vine and Matthews found, that in Pacific, Atlantic, other places of the world, the cross-section of the material shown here as N and shaded, that there is changing polarities, would give rise to the observation shown as up and down oscillatory magnetic measurements. You could find those if you allowed for the fact that the polarity of the Earth's field was actually changing. While the material was essentially the same material being made, it was the magnetic field changing. And they wrote, the theory is consistent with, in fact, virtually a corollary of current ideas on ocean floor spreading and periodic reversals in the Earth's magnetic field. If the oceanic crust is formed over a convective upcurrent in the mantle at the center of an oceanic ridge, it will be magnetized in the current direction of the Earth's field. Thus, if spreading of the ocean floor occurs, blocks of alternately normal and reversely magnetized material would drift away from the center of the ridge and parallel to the crest of it. And there is one of the biggest discoveries made in plate tectonics. And part of the reason this paper is so famous is because they were correct. So if you look in Wikipedia for a textbook view of explaining this process, it starts with sort of a profile, a three-dimensional view of magma upwelling with new seafloor being made. So we want to start back at the top here, and the normal magnetic polarity, such as today, is shaded the colors, and when it reverses, it's shaded white here. So it starts in panel A with the seafloor spreading apart under normal magnetic polarities. As time goes on, we have these reversals to form the white patterns, new material forms here at the spreading ridge. And as this time passes, new material continues to be formed here, and the striping is measured in the form of magnetic measurements of material at the seafloor. This all lends itself well to an animation to kind of see this, but really there's two things going on. One is that the Earth's magnetic field is flipping in polarity, while rocks are being formed. It's the same rocks, nothing magic. They're just preserving a different direction of the magnetic field. So we'll look here at an example of this. And so here what we see is time going on. So just schematically, tens, millions of years going on. And when the Earth's magnetic field polarity changes, the signature in the rock record changes as well. So here it's red, switches to blue, back to red, to blue. So we'll watch this one more time, but basically as the new material is being made here and time is marching on, the reversals of Earth's magnetic field give a different signature to the rock. So it's pretty much the same rock being formed and cooled, but it's preserving a different magnetic field. So here, new seafloor is being made under the blue. This will switch back. And so we get this striping pattern. Now keep in mind, it doesn't mean that the rocks are blue and red on the seafloor. This is just to highlight the fact that they would have different magnetic properties. All right, so back to offshore Washington, Oregon, British Columbia. We had this 1961 view of the data set, which clearly inspired a lot of authors to understand this region. So we have the data, and then following Fine and Matthews 1963 and other ideas at the time, we have this evolving interpretation of what was going on. And then finally, in its full glory, the colored picture at the end. So we'll step through some of these examples. 1965, this was looking at a paper by Wilson, who looked at kind of the bigger picture of plate tectonics in the region, saying, well, here's spreading happening, but we also have to think about the San Andreas fault system as a strike slip fault system, and the Queen Charlotte fault system also in this same picture. So had a very big picture view. And when looking into the region of this Juan de Fuca region, you see Juan de Fuca Ridge here, and kind of a schematic view of trying to understand this region, including the Queen Charlotte fault. Vine similarly investigated this region and wrote here, arrows the axes of 3 short ridge lengths within this area. So we have one arrow here pointing out the Explorer Ridge, this pair of arrows here pointing out the Juan de Fuca Ridge, and this arrow here pointing out the Gorda Ridge. So understanding this pattern, but still you can see how linking the actual stripes to ages is such a critical step. That takes us back to the 1968 publication showing the figure. And really the key point now here is the age linked to the items in this field, and that the red anomalies here coincide with the ridge crest, Juan de Fuca to the north and the Gorda to the south. So we can see here, once we know where the ridges are, the active spreading ridges, we can kind of put arrows on this and start thinking about linking this to the plate tectonic setting. The seminal paper gives us an idea of understanding the configuration as we know it well today. And the first step here is to draw a plate boundary. We know the spreading ridges are connected by these active transform faults of strike slip. So here's spreading ridge 1, 2, and 3. We can use that to help define the Juan de Fuca plate. We also know now that the plate subducts under the Pacific Northwest region in Vancouver. So here we have the boundary of the Juan de Fuca plate, and the seminal work on magnetic patterns helped illuminate the plate tectonic setting of seafloor spreading between Pacific and Juan de Fuca, subduction of Juan de Fuca beneath North America, and also right lateral strike slip faulting between Pacific and North America on the Queen Charlotte fault, and also, of course, to the south, consistent with the San Andreas fault. Finally, it's this magnetic striping pattern on the seafloor that enabled this spectacular picture of mapping the age of the entire seafloor. So these are not the magnetic stripes, but by recognizing and measuring the magnetic stripes, and linking them with geological time from other measurements of rock ages, we can see clearly here just the picture and pattern, with the reds representing the spreading ridges where new plate material is forming. And then, when it reaches other areas like subduction zones, it's disappearing from the Earth. Takeaway topics. The Earth's magnetic field is created by convecting liquid iron in the outer core. Didn't talk about this, but we should start with that understanding. The Earth's magnetic field flips its polarity a couple times every million years. Molten rocks cooling at spreading ridges preserve the direction of Earth's magnetic field at the time they cooled. This was put forward in 1963 by Vine and Matthews. As the seafloor spreads over millions of years, the creation of new rock and the reversal of the magnetic field forms a striping pattern of magnetic anomalies, with this convention, solid being the positive normal polarity today, and white being the times when it was negative or reversed.